Oh. All right. So we'll continue with talk by Daniel and
yeah.
All right.
This. Okay, so I really appreciate everybody who's still here. Wants to listen again. I'm gonna. So I was just explaining the quantum GIT conjecture. So this is, I guess I should have said explicitly, this is, something or Teleman. Well, this is a quantum cohomology implication of Teleman's ICM paper. And if you recall, so we had this action of the Coulomb branch algebra, and we intersected with this identity section, and that's supposed to give you the quantum cohomology of this. If you're in the Fano case, if you're a symplectic geometer, the anti-canonical reduction, assuming that's right. In some cases, it may not be. So concretely, in the abelian case,
last time you were making the point that this loop group version is only a module, not an algebra. So what does the
say that again?
The definition of the quantum homology, the equivariant quantum homology with respect to the loop group function, only gives you a module of quantum homology, equivariant quantum homology of M.
This one here is as the statement is as this conjecture is as rings. So when
so you just drop the.
So I'll come to the state of affairs of everything in a moment. So and this would be the statement in the abelian case. It's just that as rings, you just set the Seidel operators equal to 1. And so I just want to say, what is this? I didn't have time to go over it last time. What does this unit section actually mean? So you recall last time I had this presentation I explained how one actually computes these Coulomb branches explicitly. So the algebras I start with the maximal torus, and that's the algebra with elements z plus minus and this tau. And then I join this U, which is this affine blowup, this Bezer-Kovnikov, Finkelberg, Mirkovich description. So you have this blowup, and then I get this explicit hypersurface. So now to get the unit section, that's just going to be the fiber where so basically if I I take Biel invariance, the unit section that I'm looking at is going to be where it's a copy of H star BG. So what is it? Well, it's just when I set all of these. So I'm gonna if I set x equal to 0, basically, then basically it's a copy. You have a copy of H star of BG, which in this case is generated by this single element. So if you look at the fiber over 1, it splits into 2 copies. One is where this x is equal to 0, and one is where this sigma is equal to 0. So it's again some explicit. This is not some like abstract thing. You can actually compute what these tensor products mean. So the theorem, this is kind of the main theorem that we've proven, I'd say, is that in the abelian case, this works without any assumption that this works, and moreover, there's a stronger theorem, which is that the equivariant quantum cohomology is actually a free module of rank, the cohomology of the quotient over these Seidel operators. And the theorem, the conjecture is true. I mean, as rings. So this is actually a ring homomorphism. There's a ring homomorphism from here to here, and it's actually an isomorphism. That's our main theorem. So So the homomorphism, the actual map, is just this quantum Kirwan map that I described in lecture 1. I'll review it again a little bit later. The main contribution is actually to describe the kernel. And as I mentioned last time, the proof uses Hamiltonian fluid theory. At least that's the proof that I know. And so in the non-abelian case, so far we can only prove things under an assumption, which is this, what I called the G monotone assumption last time. And what it is you take the coadjoint orbit of this element 2 rho, and you look at its convex hull. So that's some convex set that contains the origin. And as long as there's no points with positive dimensional stabilizers that map into that convex hull, so there's no stabilizers. There's no points with positive dimensional stabilizers that's too close to the origin. So concretely, again, for SU2, what you would be doing is you want to avoid fixed points that have weight 1 or 2. So as long as for the maximal torus. So as long as the fixed points have higher weights, then you're good. If you have fixed points that are too close to the origin, we're still have some trouble. I'll explain why in a moment. There's kind of a fundamental reason why we have trouble in that case. And again, in that case, the conjecture holds. I still believe the conjecture in general, and I'll explain my strategy that I hope to execute. But it's more complicated. It's fundamentally more complicated in that case. So this is some fun with nano banana. This doesn't mean anything. It's just showing that in the case of SU2, you can visualize this very concretely. That basically whenever you have these images of moment maps, you should always think about what's happening for the maximal torus. So the Lie algebra of SU3 is actually three-dimensional, but there's you can look at its image to the maximal torus, which is one-dimensional. And so we want to make sure that when you take this part and you look at its coadjoint its image under conjugation, the full Lie algebra, there's no fixed points that map into that region. So again, let me just go over one thing about how you can compute in general. So I said the computations are not that bad, assuming the conjecture is true. This really does give you a way to compute quantum cohomology. So I want to review a classical fact due to Sean Martin. It's Martin's abelian non-abelian formula. So let's say you have some G action, and you know that both the reduction by the torus, the maximal torus, and this reduction by the group are both smooth. Then there's this element here that you can write down, which is, so you choose some decomposition into positive and negative roots, and you can write down this Euler class in the cohomology of BT, and basically it's Weil anti-invariant. So you can look at its quotient. You can define the annihilator of this as acting on as a map from the Weil invariant part to the Weil anti-invariant part. And the theorem due to Martin is that you can calculate the cohomology of the G quotient as the quotient of the T quotient by all things that are annihilated by this element. And what I want to say is that the quantum GIT formula, whenever it holds, it implies an abelianization formula. So it's kind of almost equivalent to this abelianization formula. And it comes readily out of the geometry of these Coulomb spaces, branch spaces. So let's go back to this. So for SU, to explain what I'm saying, so the statement is, again, basically you look at the quantum Kerwan map, you look at this, the image of this element here with the same exact formula. And then the cohomology of the G quotient is given by the quotient of the Weyl invariance of this quantum cohomology, the T quotient, by this annihilator. But of course, understood with respect to the quantum product now. And what I claim is this comes out in a very straightforward way from the geometry of the Coulomb branch. So let me explain why. So basically, if you look at this, the T quotient before you take Weyl invariance is basically looking at the fiber over 1. So as a module, that this fiber so splits into 2 irreducible components. And what we're doing is basically quotienting out by one of the components and leaving the piece, the intersection with the branch, which is the unit section. So basically you have an irreducible fiber in the after you blow up, and then the piece that you're left with after you quotient but you're kind of killing this piece, and you're left with a piece that is the formula tells you should be true. So basically, this relationship of the total spaces encodes this Martin formula. So all right, so that's maybe like why you might be interested in this subject. But let me explain our new approach. So this is now we get to some actual geometry that's very related to Umut's talks. So the way that I'd like to think about this is that the Floer cohomology. So the way that I want to relate these spaces is by relating. So I take some normal neighborhood. So basically, the quotient inside of my M, the normal neighborhood is a fibration over the quotient with fibers that are symplectomorphic to subdomains of a cotangent bundle. And you can write down a version of a vertical version of equivariant cohomology where you just kind of count curves. Equivariant symplectic cohomology, so you're wrapping in the fiber, but you're only going to count curves that are sort of vertical, that project the points in M mod G. So, or depending on how you set this, almost points. I mean, there are different ways you can set this up technically. I'm going to kind of ignore the technical detail. The idea is that we have sort of a vertical version of symplectic cohomology. So this is very easy. In the abelian case, what you want to think is that you just have, you're looking at, say, mu squared as your function, but you're only considering orbits that are inside of your neighborhood. And then it basically is because these fiber-wise, these live in different connected components, you just get a disjoint union of copies of the quotient, basically. So, but in general, for a general G, it's a little bit more complicated. What it computes is there's sort of this. You look at the space of loops that are that project to points. So fiber-wise loop space, and then you have a parametric version of Viterbo's theorem that says that the cohomology of this vertical symplectic cohomology is just the shifted homology of this the space of vertical loops. So that's the starting point. And then I want to sort of view my quantum cohomology, my ambient space, as a deformation of that. And well, so my strategy for doing that will follow very closely a paper of Umut and Nick Sheridan and Borman, that does this in sort of a related thing in the or affine varieties. So they kind of view symplectic cohomology of a projective compactification as a deformation of the symplectic cohomology of sort of, you know, you can think of it as a Liouville subdomain around the skeleton. So this is some kind of version of that. So let me sort of say that. What?
Result by itself already the slide is parameterized without result. Is this written or just you're guessing and it must be true?
Oh, it's in my unpublished manuscript that's been in progress for way too long. But this is something when I prove. Yeah. Yeah. I mean, the abelian case is straightforward. It's sort of there's no differentials possible. Like just like abelian version of Viterbo's theorem is straightforward. So the basic idea, so I'm going to look at the abelian case, is to use a T equivariant. So we're going to look at T equivariant Hamiltonian Floer theory of k times the norm squared, but as k goes to infinity. Well, I have this half factor to make things work out. So Kirwan's theory, you know, Moore's theory, like at least you know, heuristically, Moore's theory corresponds to k equals epsilon, like for epsilon small. And but I want to consider the other limit where you're looking at k goes to infinity. And you know, of course, these Floer complexes, just by the definition, are just they're all sort of isomorphic. But of course, the periodic orbits are changing a lot. And so, as a first approximation, so the reason I'm saying that this is, like, by the way, related to symplectic cohomology with supports very manifestly is if we look at what this family is doing. I mean, this is kind of an ad hoc version of symplectic cohomology with supports. I don't consider all, you know, this more. This is sort of a concrete way to realize it. Yeah.
It's like a background question.
Yes.
There's an acceleration map from cohomology and symplectic cohomology. So
Yeah.
is there an acceleration map from cohomology with support, symplectic cohomology with support?
Cohomology with supports.
That's like, you know,
There's a
sheep
map
cohomology.
cohomology.
No, not like sheep cohomology.
This is no supports. This is just standard. This is just like, I'm just doing ordinary at the moment. I'll get to supports.
Okay. Yeah, I was just never mind.
I'll get to supports later in my talk when I try to explain why, you know, when we look at why this works here and doesn't work, then we'll see that supports is probably the right way to think about things. But for now, I'm not completing anything. I'm just looking at this telescope. But so you have to prove one thing, which is that for orbits inside of n, inside of your normal neighborhood, then the Floer theory on M is a deformation. So what does that actually mean? So you have to choose some, you choose some caps, which in the abelian case will basically be such that the Robin-Solomon indexes of the orbits are 0. Or these are fractional cap. So the model for Floer theory in this monotone case that I'm using is basically I'm just looking at a one variable Floer theory where the caps are, basically considered up to their area, and then I have to make them fractional to make sure that I have sort of enough of them to do what I want. But when I choose it so that I choose these caps so that the Robin-Solomon index of these orbits is 0, which is what they should be from the point of view of string topology, I over Y string topology. Then the result is that the Floer differential, all the powers are non-negative that appear in the differential, all the Q powers. And this is not obvious because Q is not this. If you do this with Novikov, in the Novikov setup for Floer homology, then the area energy is always positive. But in this case, that's not immediate, but it's true. So you have to make some assumptions about how it's the analog of what happens in what one has to prove in the Foreman, Sheridan, Varolgunes work is that Flory trajectories actually intersect the divisor positively. So, and then, but there's some way to do this in this setting, and you have to make some assumption about how you have to make some assumptions about how basically you want the almost complex structure to project, or you can be arbitrarily close to this, but let's say project to the quotient holomorphically and to be kind of in the fiber-wise sort of convex. And then for those class of complex structures, this result is true. And so we get this deformation statement for those generators that lie inside of the normal neighborhood. So maybe I can draw a picture of what's going on. Of course, the problem here is that there are many more generators. There's too many generators. There's generators at a fixed point. There's a very simple example that illustrates a lot of stuff, which is just looking at P1. So this would be like a very simple case of what I'm trying to do, but it already illustrates kind of what I'm talking about. So we have, so if we're looking at a small enough slope, so k equals epsilon, I would basically just have, and I'm looking at, in this case, I'd be looking at, I'm not looking at the moment map itself, but I'm looking at epsilon mu squared as my function. And so the critical points of this kind of Hamiltonian, there you have the fixed points, but you also have some circle. That's Kirwan's story. And then when we let's say we increase k, then these fixed points will stay there, but then I'll also get these, some additional circles, right? And the higher k is, so this would be k, I don't know, going basically past 2 pi, maybe my 2 pi plus epsilon, something like this. And then if you do 4 pi plus epsilon, you get more and more circles. So as you go in here, you're really looking at symplectic cohomology of the interior, but you also have these kind of generators here. And you want to show that those generators don't count. And this in toric varieties case, this is exactly what Umut proved, or Umut and Nick proved. And the claim is that if you just look at what they did, then the same argument works in this case. But we'll have to use, obviously, some assumption. So let me explain that. So we want to filter this complex in a way that we can kind of just say that these kind of orbits that are always at these fixed points, in this case, don't contribute. And the way to do that is to look at, which is an idea I got from their papers, to look at the monotone index. And what this monotone index does is it's something that you can only define for monotone symplectic manifolds. If you look at the degree of what you're dealing with, of your cap orbit, and you take away twice the action. And that turns out, because somehow you're looking at something monotone, if you switch it by a sphere, if you change the cap by a sphere, so the space of caps, the torso over like H2, then the degree and twice the action will change by the same amount in this case. So this is well defined. It only depends on the orbits themselves. And so the statement is that in this balance, specifically if the moment map is balanced, one has an estimate like this. So there's a constant that's independent of k, for which this mixed index is always bigger than or equal to k mu squared plus this constant. The constant is basically the dimension of the manifold. I'll show where this constant comes from in a moment. So this is kind of the key fact for this monotone case. And where does it come from? So the key point is that the moment map is when you have a let's say you have I'm looking at G as S1 in this case. And the same thing will be true for every, if you have a torus, it'll be true for every subtorus simultaneously. So the point is, if you have a fixed point of an S1 action and your moment map is balanced, then the value of the moment map is minus the sum of the weights of the action on the normal bundle. And let's sort of think about why that's good, because sort of the action of, let's say you have a fixed point, the action will be, by definition, you're just looking at a constant cat. So the action will be the value of the function at that orbit. I didn't really say what action was, but Uma's been doing a lot of action stuff. But yeah,
Because it's important. Can you minus what is balance means?
it means this. Okay.
Oh, there's a concept.
Yeah. So it means that so the moment map returns equivariant symplectic class by definition, and we want that there's also an equivariant first term class. We want those two to be equal. So monotone means that's true without equivariance, and we're lifting that to an equivariant condition. It's equivariantly monotone. And so what you get is that now the degree, like you have a slice theorem for S1 action. So like for a fixed point, you basically are doing this local calculation of Conley-Zander indexes, which is well known, and that basically depends on the weights of the fixed points so the Hamiltonian, the amount of rotation is basically just k mu, and then you're going to multiply by the weight. And so the fact that the weight and the moment map are equal mean that these kind of differ by a finite amount. That's sort of the idea. So okay. So what you're going to do is you're going to take, so we want to choose some delta. Sorry, my slide got with delta less than the maximum of mu squared over n. Okay, so I have some normal. I fix some normal neighborhood at the outset, and like let's say this, I'm looking at the P1 case. That means I'm just fixing some range around mu equals 0. And I'm going to fix some delta, which is less than the maximum mu squared over this region here. So something a little bit less than the size of my normal neighborhood. And then I'm going to look at a subcomplex for every hi that appears, all these slopes that appear in my telescope. I'll look at I'll also fix some number p at the beginning. And we'll explain what p does. And I want to look at all things whose action is bigger than or equal to p minus this ki delta. And then I further want to, so I look at the subcomplex, but I also want to truncate the degree. Okay, so what this inequality is telling me is that as long as so this inequality is something about if I bound the degree, I get something about the action. So, and I think this is a typo. This should be like 2p. I apologize for that. This should be 2p. But basically, if you look at what this means, the only things from the inequality, the only things that can satisfy these conditions are things that lie inside of the normal neighborhood. That's the so if it's with 2p. And what that means is so that what I want to do is after I take this, my final definition is going to be to take an inverse limit over all these complexes that are all p. This is exactly what Umut and them did. And the thing that you have to prove is that the cohomology doesn't change when you do this. And that's going to be basically the conditions that I've told you are basically, you know, it's not too bad once you set things up in the right way. It's not too hard. The point is basically that this action cutoff that I look at, if you look at it, it looks kind of bad, but it's getting more and more generous as k gets large. So basically, I'm truncating, but you know, as k gets large, I'm allowing more and more negative. So eventually, I allow all things with action going to minus infinity, all ranges, and so from that and some algebra that you have to do, you get that the cohomology doesn't actually change. So I'm eventually allowing all action ranges. So that's nice. But there's one kind of technical issue, which is that, I mean, the truth is you don't actually need to do this. It's a nice thing to do. For what I want to do, I didn't actually need to do this last step of looking at the homotopy limit here, because what would happen before the homotopy limit is that you would compute everything up to a given degree. And you know, quantum cohomology is actually periodic, the way that I've set it up. So it's kind of the same in every even degree. So if I can compute it properly in any even and odd degree, that's already fine for me. But you know, it's a nice thing to do. But if you do this, you introduce for yourself a little technicality, which is that you know, this homotopy inverse limit involves taking a direct product, and so your action filtration, this kind of q-adic filtration from, so I said you use we have these positive q powers. Once you've chosen these caps, it's no longer an exhaustive filtration because you've taken this product now. But basically, another thing you get that they prove very nicely in BSV is that if you look at this inclusion of kind of the union of all these q bigger than or equal to L pieces, then that's a quasi-isomorphism anyway. Then that's, it basically boils down to this fact that degree-wise you're fine up to any given degree. So, but anyways, the point is that it's nice to have a spectral sequence that computes everything. So the bottom line is that the q-adic filtration here gives a convergent spectral sequence. Now with the E1 page in this case, it's as I was saying, in general, it should be this fiber-wise symplectic cohomology, but in the abelian case, you know, you just what is your fiber-wise symplectic cohomology? It's just the cohomology, the quotient, and then a bunch of different copies of that because you know there's no differential between different strata just for homotopy class reasons, and then that converges to this equivariant quantum cohomology. Now, here's where things get better in the non-abelian case compared to the where things get better in the equivariant case compared to the ordinary case. So I can illustrate that for this, you know, you can illustrate that very well in this toric varieties case. So in the toric varieties case, we know that, like, what should the spectral sequence be computing? It should be computing in that case, the spectral sequence from the cohomology of the torus, symplectic cohomology of the torus, to the quantum cohomology of the compactly projective toric variety. In that case, there's some differentials that arise, but in the equivariant case, all these circles are really points because, like, you know, the leading order differential, the thing that's already in this E1 page quotients this circle into a point. So everything is actually in degree 0. So the spectral sequence automatically collapses. And what I claimed is that there's something like that that's true in general, as a general fact. So why is that a general fact? Well, let's say, and that has to do with this classic, we're going to invoke classical curve unsurjectivity. So what I claim here is that basically this strata, you what's making the spectral sequence, the mechanism behind this degeneration is Per-1 surjectivity. So if we look at, we take some kind of thing in, corresponding to the constant orbits here, and we're going to lift that up to some, we imagine there's some cocycle in that hits that at the, let's say at the cochain level. Then my claim is that if you make your data, your choices appropriately, then like your PSS snaps, I'm imagining like a PSS homomorphism from something like this to this. So at least to leading order, what I claim is that this just gets carried to this. Okay? And then the higher, there's some higher order terms possibly, but those lie in some piece that's bigger than, that's in positive Q power, strictly positive Q powers. So basically what that means is that I choose some lift, which is actually a class, then I can generate these in my spectral sequence, as far as my spectral sequence goes, I can generate these constant orbits. So I have some spectral sequence and I have some piece here that I claim survives the spectral sequence. And then from that, I get that, like, what is this really doing? What are these operators? I claim that they're the leading order terms of the Zeidel operators. So the Zeidel operator, what it does is, at least like the leading order term will just take like this to this. It will just, the shift operators will just kind of move these around to different homotopy classes. The leading order. So as far as the spectral, so what I claim is the action of the shift operators on the spectral sequence is just the natural action of Z. So putting those things together, what you get is that in this case, the spectral sequence actually degenerates. The E1 page. This is not actually needed for the quantum GIT conjecture. All we need here, as far as this goes, would be that it's just the spectral sequence itself, but this gives you this extra fact that it's actually a free module. So just the spectral sequence alone is enough for this. That's all we really need for the quantum GIT conjecture, because I'll explain in a moment. But it gives you something. The degeneration gives you something a little bit stronger. Okay, so what it's sort of interesting to think about orbifold case. So for orbifold, this gives something really cool as well. So for orbifolds, like the picture really gives you like a very clear idea of what's happening. So let's think about what the periodic orbits of k mu squared are of this near mu inverse of 0. So what you'll have is as before, these periodic orbits that appear, these families which are circle torus bundles over the quotient, basically copies of mu inverse of 0. But you also have these exceptional orbits, which lie over. What do they lie over? They lie over places where there's infinitesimal, where there's finite order stabilizers. And so the claim is that what happens in this case is that the spectral sequence is now giving you the orbifold cohomology of this quotient instead of starting with the ordinary cohomology, you're really looking at the orbifold cohomology of the quotient. Now I don't know how to prove this degenerates in this case because you don't have Kerr-1 surjectivity for orbifolds. It's a fundamental point, actually. And you think about it, it's not Kerr-1 surjectivity. This shouldn't be Kerr-1 surjectivity because like there's an action separation that actually happens here. Like the orbits sort of, you have the constant orbits here, but you also have like what's the first version of these like things with finite stabilizers? It comes at a strictly higher action level. They're like half orbits. But they appear where the Hamiltonian vector field is actually rotating, but half as much. So they're not really something classical necessarily. But in cases where, like for toric varieties, for example, for toric orbifolds, then everything's like usually even degrees, and then you would get degeneration. But in some cases, degeneration would just follow from like the evenness of cohomology, but I don't know about a general state about degeneration in this case. It's probably true. I mean, actually, I can give, if we can fantasize a little bit for a second. I mean, maybe this is already fantasy, but like the idea might be that when we quotient, there's basically you can imagine a model for equivariant cohomology because we've made it so that all our orbits lie where there's finite stabilizers. We can imagine that instead of doing things over the Borel space, we actually do something where we quotient the generating sets, and we also quotient the moduli spaces. So there's a version of like Bucayas has constructed a version of Lagrangian fluid theory this way. And then you can imagine that there's like, you want to somehow use that there's an additional rotation action on the moduli space. This is like something that appears in work of Bourgeois. It's a little bit fantasy, technically, but you could, if that works in this setting, that would give you that would give you another way to prove the differentials are zero, and it would imply that the spectral sequence generates. So I suspect it does degenerate, but we need some new arguments to prove that in this case. In the orbifold case, but in a lot of cases it's sort of okay because everything's even, and that there's no possibility for differentials. So okay. So let's go back to the argument. Let me just review where's my timing? When am I supposed to end? 20, 15?
Yeah.
Okay. So let's just recall. So we recall that we had this map, this isomorphism using the moment correspondence to the quantum cohomology. This was true in the monotone case without any bulk deformations. And then the way that I set up the map, this Kirwan, my version of the Kirwan map was just looking at this. We'll take the closed open map from here to here, and then map it into there. That's what I claim should be equivalent to Woodward's version of the Kirwan map. And then here, the reason that the Seidel operators act trivially is kind of manifest because in the Picaya category, what the Seidel operators do is just the Lagrangian monodromy under the actions. Anytime you have an invariant Lagrangian, the Seidel operators. So there's some issue about. Something I've been sweeping under the carpet. There's an issue about the signs here. So it's possible that you could get -1 and you'd have to. In this quantum GIT, there's a possible there's something that can happen with signs where you have to sort of switch the sign of your Seidel operators. But let me sort of ignore that. The Seidel operator is either plus. You can always arrange that it's 1, and then that will tell you that combined with this result so I know that this map is surjective just by classical Kirwan surjectivity. So, and then when I quote, I know that my rank, let's say I didn't even know this degeneration statement. I know that my rank is at most, when I quotient by the Seidel operator, my rank is at most this, so that tells me that that it has to be an isomorphism, that I just need to mod out by the Seidel operators. So that's nice. So that's the monotone torus case. And then from here, this was the state of affairs like for about 3 years. I don't know. After I read Umu's paper, then there was some writing, but basically, recently I've been rethinking about it, and there's a kind of something you can prove. So this is this sort of non-abelian case. If I have 15 minutes, maybe I want to jump to. I'm going to jump ahead a little bit to say something that's clearly wrong, and who's going to yell at me. But so anyways, I have some strategy now to try to do the general case. So the general case. So basically, what I want to do is I want to look at So in this monotone case, there's an equivariant version of you can set up an equivariant version of this symplectic cohomology with supports. So my Nova covering, by the Nova covering, I mean in the monotone case, I'm just looking at power series over, polynomials over Q. And what I claim is that this deformation strategy should work for this symplectic cohomology with supports. I want to prove 2 statements. The first would be this one, that I can get the spectral sequence and that it will really converge to symplectic cohomology with supports in general. And then I want to prove the second thing, which is that sort of so it's not going to be the case that even though I've set things up in the Z-graded way. So what I previously proved, I think, could be thought of as saying symplectic cohomology. This version of symplectic cohomology in the abelian case, symplectic cohomology with supports is isomorphic to quantum cohomology. That's kind of, I mean, with this version of symplectic cohomology with support, that's kind of what we proved. What I would say we proved. But I want a spectral sequence that actually converges to this. And then I want to prove that what the effect of taking the relationship now is given by the following. So I'll look at this Coulomb branch. So the difference in the non-abelian case is that the Coulomb branch algebra has negative degrees because it's really looking at a loop space. So it has a lot of negative degrees. But when when I'm doing this Fleur theory stuff, I'll adjoin this Q plus minus, in particular Q, and I kind of have to, when I take the graded Q completion. And what that does is because I have a bunch of stuff with negative degrees and a bunch of stuff with positive degrees, then you'll get some completed algebra. Okay? So, you can think of it as 2 periodicitized. And what I claim is that this version of symplectic cohomology with supports should just be given by completing in this way. But what this, from the point of view of the fiber over this identity Lagrangian in my Coulomb branch, this completion is harmed. So when I tensor, first of all, I'm going to prove that when you tensor this with the identity, you get quantum cohomology of the quotient. But from the point of view of that Lagrangian, I'm kind of completing things near that Lagrangian. So I've lost a bunch of stuff, which is what we call this kind of trapped cohomology. But I have from the point of view of the identity section, this won't change the tensor product. I think this should be the mechanism in general behind this sort of algebraic version of the quantum GIT convection. So what's this monotone version. And then now I'm going to say things that don't look really well, No, anybody can say. I haven't. Yeah. No, I'm going to say more. I'm going to say.
Should I leave?
No. I'm actually curious. I'm very curious. So this is what I claim we want to prove in general. But really, I think the point is actually that the real point is that it's wrong to try to do things that have been stubbornly trying to do things algebraically over this polynomial Novikov ring. We should really be looking at the universal Novikov ring. So this is something that I have more like either I call it theorem in progress. I think either I have a strategy to prove it or it's wrong. Yeah.
How do you deal with like anti-Borel stuff that compass operate?
Well, I mean, that's not a problem because when you invert Q, you're looking at over the Borel space. It's just looking from U with this invert limit. So this thing about Borel is not a problem. I mean, it's really not wrong. I mean, because polynomials in Q. What I'm saying is like if you do this is not an obstruction to what I'm trying to do. Like this will not be the same as like doing it the other way. So there's no spectral sequence of the conversion spectral sequence of the kind that you're imagining.
Sure, I'm sorry.
Yeah. This is not an obstruction. So either I can prove this or it's wrong. So that's what I mean by. So I thought about this, but I still haven't written down all the details. So that's why I say theorem in progress. So either I have some way of doing this, or it's just wrong. I'd like to know other. I'm going to keep looking at it, but I think this is the right thing to do geometrically. So instead, we're going to look at this. Let's say you don't have a balanced moment map, and we're going to work over the universal Novikov ring, and I'm going to just look at the kind of ordinary symplectic cohomology with supports that we've been looking at for this whole workshop, basically, all of the talks, and I'll do my construction, but compatibly with this filtration, and then the theorem, which I said either my proof works or this is wrong probably, but is that there's an additive identification of this LT equivariant symplectic cohomology with the quantum cohomology of the quotient. And then again, if all this Ukaya Lagrangian correspondence story is completed, then you'll put the bulk parameter that I mentioned in my first lecture here, and that will be a ring isomorphism. So, and I'm not, again, I'm sort of a monkey, so I'm copying things I see, and there's things like this. I didn't complete my my first page. That's hard, but the I want to use the Novikov filtration instead to write down the spec. Yeah, let's just ignore that. I'll write my first page. Yeah, I was trying to do this over lunch, but I was talking. I got caught up in a discussion. But the first page of the spectral sequence, what it is, it'll be again. So I'm going to fix some h and some small h, and I'll filter by powers of this t to the power of this small h, and so the first page will be the EPQ will be the cohomology of M with M mod t. So basically the tensor Q. Let's say I'm working over Q. Z plus minus, and then the t powers that lie between like t to the like p minus 1h and t to the ph. So there's some very nice work of Yoel Groman and Yuhan Sun that construct sort of ordinary. Yeah, sorry, this slide is a disaster. I apologize, but they do this for non-equivariant they do versions of this for for inclusions of Liouville subdomains in non-equivariant symplectic cohomology. So, and if this kind of spectral sequence does exist in the way that I think it does, then my previous argument will basically prove that the same argument as before will prove that the spectral sequence degenerates. So just to give some indication of what I'm talking about in a concrete way, so maybe I can. So let's say we're looking at, let's do an example situation. So let's say I'm looking at CP1 with an S1 action. Then over the Novikov ring, the equivariant quantum cohomology looks like this. Okay, it has these relations here. And what I want to do is, so if I norm, so I said, so in this T, when you work over the Novikov ring, there's some, you're normalizing using the equivariant symplectic form. So you basically normalize it so that the shift operators are action preserving. So the shift operators become, if I look at mu equals 0. So my moment map, I'm keeping it as going from -1 to 1. And I'm kind of in the middle. I'm looking at the middle. And what I have here is my shift operators are x over q and y over q. And then the spectral sequence exists then for this, because again, there'll be everything will be even degrees. It'll degenerate. Actually, what I'll get for this equivariant symplectic cohomology with supports will just be a topologically free module over the shift operators. It'll be topologically generated by like the cohomology of the circle modulo S1, and then complete it because you're going to be working with the spectral sequence you generate. It'll converge to this completed thing, and that's what you'll get. And then you can look at other values of the moment map. So what have you done? What does it do in this case? So you can still specialize S equals 1. That's valid, but somehow you kill other. So in the original algebra, you could specialize your S variables to anything between 1 and t to anything, like you can specialize to any t to the alpha, where alpha lies between 1 and -1. And here you're just kind of completing it at S equals 1. And then for different values, it'll be a similar story of the moment map, but you'll be able to specialize it exactly that, like S equals 1, but it'll be sort of renormalized S. So from this perspective, you'll specialize S equals t to the alpha, for some alpha. So this is exactly what comes out of the Gonzalez. This is exactly the completions that appear in Gonzalez and Woodward's work. You can match that up. So then there's one more piece of speculation, since I'm at the Miami conference, which is that what I hope is that this reproduces completions that appeared sort of ad hoc in Iritani's work on the blow-up formula. So in this case, you have a smooth subvariety, and you're gonna look at the blow-up of x cross p1 along z cross 0, and you're gonna look at the S1 action on this space, and so you have two quotients that are in this case, which is a very simple GIT problem. You have one quotient, and you have one quotient which is the blow-up, and the other quotient which is x. And what Iritani does, or part of his his theorem has kind of two steps. One is to do this kind of Fourier transform quantum D modules business, and then one is to kind of decompose this further. But let's say this step is sort of an important step. So he constructs sort of completions of the quantum D module, which are sort of completions of submodules here. And they're different completions that correspond to different GIT chambers. So what I want to say is that the symplectic cohomology with supports at the different corresponding to different level sets should give a more conceptual definition of these completions. Of course, there are like different Novi couplings that are like here. He has a kind of I'm kind of using the universal one, but here he has multivariable Novi coupling. So the question would be like, assuming everything checks out, can we compare these two frameworks? And I think that's a reasonable place to leave things. So hopefully you can understand why my title, everything in my title has appeared. So I'm done.
Thank you.